Now we have the formulation to be made for calculating the Carnot efficiency. Carnot efficiency is the maximum efficiency that a reversible thermodynamic cycle can achieve. So whenever we talk, it is not 100%, but it is the maximum efficiency that we can achieve. For instance, if we develop a certain thermodynamic circuit and thermodynamic process, and we want to calculate its thermal efficiency, the maximum we want to calculate the maximum efficiency that it can achieve. So we calculate the Carnot efficiency, and we say that it is the maximum efficiency that this system can achieve. Obviously it will have losses and other parasitic aspects, and this maximum value decrease by many fold, and a few percentage of this efficiency or energy will be available at output. But when we wanna estimate that how much energy will how much efficiency this particular any thermodynamic cycle can have, so we talk about Carnot efficiency. We already know that the heat transfer is always proportional to the temperatures of the reservoir. So for instance, we have two scenarios. If we want to understand it, if let us have a copper block that is at 1000 degrees centigrade, and we place it in the room temperature, and then there's another copper block that is at 100 degrees centigrade, and we place it in the room temperature. So the rate of heat transfer from the 1000 degrees centigrade copper block will be definitely higher than the rate at which the energy is being transferred from 100 degrees centigrade copper block to the room environment. So temperature heat transfer is always proportional, is always function of temperatures of the reservoirs TH and TL. So these heat transfers QL and QH are always a function of uh, temperatures of low temperature and high temperature reservoirs. So since the its function, so the simplest function is the unity, that the and its equality, that QL is equal to TL and QH is equal to TH. It is not the function, it is a function that we can suppose, and it is the simplest one, and it will have the maximum effect. So that's why to calculate the Carnot efficiency, we take this proposition that the heat transfer is directly related to the temperature of the corresponding reservoir, and the constant of proportionality is 1. So we replace the QL and QH with TL and TH in the thermal efficiency formulation, and we get what is known as the Carnot efficiency. So if this is the thermal efficiency, and we convert into this Carnot efficiency, 1 minus TL over TH. Whenever we calculate it, we will find that this is the maximum that we can achieve. Now let us consider an example in which we consider a refrigerant cycle, and we calculate its rate of energy taken from the cold state, that is QL dot, and coefficient of performance. We have a scenario in which we input one 50 watts of power to a refrigerator, and it moves heat from low temperature reservoir to high temperature reservoir, and the heat being flown out of this refrigerator to the room is 400 watts, 400 joules per second. So 400 watts of power is being delivered to the ambience, and we want to calculate the rate at which heat is being removed from the low temperature reservoir. So it is quite simple. We know that work is equal to QH minus QL. So we can find out of this equation, and it is quite work dot is equal to QH dot minus QL dot. So we have these two quantities, and we can find this third one. And coefficient of performance, we know that the coefficient of performance uh, for the refrigerator is QL dot over work dot. So we have these both quantities, so we can find the coefficient of performance. This is quite simple. Now we do an example in which we find the Carnot efficiency and compare it with the actual efficiency. So let us have an example of a heat engine as shown in the figure, and that receives heat at a rate of 1 megawatts from a higher temperature reservoir at 550 degrees centigrade. So this is 550 degrees centigrade, and Q H dot is 1 megawatt, and reject the heat through 300 Kelvin, and work that it produces is 450 kilowatts. We would like to know the how much energy is discharged to the ambient. This one QL dot to the ambient surrounding, and the efficiency of this, and compare the efficiencies for Carnot engine as well as the actual engine. So if we find the efficiency using these temperatures Q, TH and TL, then it is TH minus TL divided by T divided by TH. So this is the Carnot efficiency, and if you calculate it, we will find it to be 0.635, and nearly 63 the efficiency, it is 63%, 63.5% efficient. Whereas if we use the information of heats that we have found in this is QL, we already know QH, so we use these heats, and we find QH dot minus QL dot divided by QH dot. We will come to note that this engine is only 36% efficient, um, and we will find that it is with the 45% typical modern steam plant. This also implies that the actual engine has much more, much lesser efficiency than the Carnot efficiency. So, as we have already discussed, that the Carnot efficiency is the maximum efficiency that a machine can have. So, obviously, the actual efficiency was expected to be lower than that value, and we found it by using these both formulation, one for the Carnot and one for the thermal efficiency of actual engine, or more ideal case. It is also the thermal efficiency we found by using the rate of heat transfers, this one is also an ideal case. It does not include the frictional loss and other. That's why it is much more than the actual mechanical efficiency that an engine have. Usually an IC engine has only 20 to 21% mechanical efficiency. So if you find thermal efficiency, it will be greater than that mechanical efficiency, and if you find Carnot efficiency, it will come out to be even more than the thermal efficiency. Therefore, the Carnot efficiency is the maximum efficiency that a machine can have. Now we consider a scenario in which we wanna maximize the thermal efficiency. For instance, if we want the Carnot efficiency to be maximum, to be 100% efficient. So what we will have, um, we have this formulation that Carnot efficiency is 1 minus TL over TS for an engine. So if we want to maximize it, we must reduce this term TL over TS is equal to 0, and we will be then left with thermal efficiency of 1. For making this term 0, either we lower the TL to 0 Kelvin, or we maximize this TH. And if we draw this curve for increasing the higher temperature reservoir, temperature of higher temperature reservoir, the efficiency increases sharply initially. However, if we further continue to increase the temperature, it steepens down, and now it is nearly the slope is much relatively reduced than this initial phase. So if you continue on increasing the temperature, it will get more uh, flattened, and efficiency will not increase. So there is a limit that we can increase this Carnot efficiency using higher temperatures at higher temperature reservoir. However, and the second case is it is impossible to generate a temperature of 0 Kelvin. 0 Kelvin is minus 273.15 degrees centigrade. That is the temperature of far field space temperature. So that is also not easy to maintain. We have certain mechanical apparatuses that is in which we can maintain our temperature near to this 0 Kelvin, not exactly 0 Kelvin, but it is not favorable. We need immense amount of energy that to maintain this temperature of 0, that is near to 0 Kelvin. So it is not the case that we can generate it for an engine. So therefore, we cannot achieve the 100% efficiency either way. So for a coal power plant, we have only 45% efficiency. It is thermal efficiency, and it is compared with the 0.6% of Carnot efficiency, 60% of efficiency. That is. Then we have nuclear plant that is only 30% efficient as compared to Carnot efficiency of 40%. Then the turbine, we have 50% efficient compared to 60% thermal efficiency. Gas engines that has 35% efficiency compared with 55% Carnot efficiency. So Carnot efficiency is maximum, and the thermal efficiency always be lower than this Carnot efficiency, and mechanical efficiency will be further lower than this thermal efficiency as well.